This paper presents a feature-preserving displacement mapping which is suitable for the GPU implementation. Using a simple base surface and a displacement map, displacement mapping reconstructs a high-frequency surface. Let's see the process of displacement mapping in the current GPU pipeline. The CPU performs expensive operations for animation and simulation on the low-resolution base surface. Then the animated base surface is transferred to the GPU. In the GPU, it is tessellated, and the vertices of the tessellated mesh are displaced to represent a high-frequency surface. In the current GPU pipeline, as can be observed here, the vertices of the tessellated mesh are uniformly distributed per input surface patch. That is, adaptive tessellation is impossible to implement in a patch. We will present a method to non-uniformly displace the uniformly distributed vertices. When the mesh is reconstructed from the base surface, it should preserve the geometric features of the so-called target mesh as much as possible. These show the cross-sections of the target mesh and the base surface in red rectangles. In the traditional displacement mapping process, first, the base surface is tessellated. Then the vertices are uniformly displaced toward the target mesh along the surface normal directions, and a high-resolution mesh is produced. However, the resulting mesh does not correctly reconstruct the feature of the target mesh. Our method displaces many vertices of the tessellated mesh toward the high-frequency features of the target mesh. Then, as you can see, the reconstructed mesh correctly represents the features. The displacement map in our method contains the information needed for non-uniformly moving the vertices toward the features. The major contribution of our paper lies in the algorithm of generating the feature-preserving displacement map. First of all, the base surface is tessellated, parameterized, and then sampled to make up a texture which we call the geometry map. Then the target mesh is processed. Its surface features are estimated largely on the basis of surface curvatures. Then the target mesh is parameterized and sampled using the surface features, and another geometry map is generated. Finally, the two geometry maps are combined to construct the feature-preserving displacement map. Let's see the feature-driven parameterization and sampling in a more detail. Consider the apex of the pyramidal target mesh. It is an evident feature. In the traditional parameterization and the feature-driven parameterization, compare the areas taken by the pyramid apex. In our method, the feature parts of the target mesh take larger areas. Consequently, the feature parts are sampled more densely and are neatly reconstructed. Compare the apexes in the reconstructed meshes. Unlike the traditional method, our method correctly reconstructs the apex. You can find the similar results in the edges of the pyramid. Feature-driven parameterization is presented in section 6.1. To preserve the features more correctly, we adopt the nonlinear sampling even within the triangle of the target mesh. In this example, the bottom edge is a sharp feature. Unlike the linear sampling, feature-driven nonlinear sampling neatly reconstructs the sharp feature. The nonlinear sampling method is presented in section 6.2. We tested the proposed method using a well-known bumpy model. The traditional displacement mapping method shows stair-stepping artifacts. But our method correctly reconstructs the shape of the target mesh. This object has many curvilinear sharp features on the surface. We compare our method with typical vector displacement mapping. Our method neatly reconstructs the curvilinear sharp features of the target mesh, but the traditional method does not. Let's compare the wireframes generated by our method and the traditional method. Unlike the traditional method, our method generates more vertices at the feature areas. This shows that our method preserves the surface features during object deformation.